Okay, so for today's Teichmüller theory seminar, we have the pleasure of welcoming Edgar Bering from Temple University, who's going to tell us about McCarthy-type theorem for large and goofy
linearly growing
outer automorphisms of a free group.
Yeah. So thank you for the invitation. It's nice to come up here on an afternoon train and talk about this stuff. So I want to start with some history and motivation for the problem that we're going to talk about. And that's really where we'll touch base with Teichmüller theory, and that we'll talk about the mapping class group for a little bit and the motivation there. And then 1 prime is a crash course in Basse-Serre theory. And then we'll introduce, so linearly growing outer automorphisms are in some sense analogous to linearly growing, well, not in some sense, they are analogous to linearly growing mapping classes. All linearly growing mapping classes are Dane twists up to finite order, and the same thing is true here. So we'll talk about Dane twists in out. And then I'll give some bad examples that foil the proof strategy suggested by the definition in section 2. And then well, by the time we're through history and motivation, you'll know what the result we're trying to prove is. I'll give a proof by example. So I'll talk through the examples that I give and why the proof works in these cases, and you can read the paper if you want the generalization. So where does this all start? Well, it starts with everyone's favorite group, GL2Z, which is by definition the automorphisms of Z2. And we can also think of it as the extended mapping class group of the torus, or as the outer automorphisms of a free group on 2 generators. So generalizing this, generalizing these 3 points of view gives us 3 infinite families of groups, and there's a long-running and very beautiful analogy among them. And our talk is going to, or my goal today is going to focus on one small aspect of this large and long-running analogy. So the 3 infinite families of groups are linear groups, which GL and Z will stand in for, but there are many other ones as you change the ring of integers. Mapping class groups of finite type surfaces, and outer automorphism groups of free groups of finite rank. So this analogy, one high watermark in this analogy is the Tietz alternative. And so definition, a group G satisfies the Tietz alternative, or you might want to say a Tietz alternative, since there are strengthenings and variations, but this is the original. A Tietz alternative if for every subgroup either it has a free subgroup, or H has a finite index solvable subgroup. So we'll say it's virtually solvable. And why is a statement like this such a big deal? Well, at the time, well, first, the name came from Tietz proved that this is true for linear groups. So yes, Tietz. And at the time, there was this long-standing, now known to be false conjecture, the von Neumann-Day conjecture, which suggested that every group was either had a free subgroup or was amenable. And virtually solvable groups are amenable groups, although not all amenable groups are virtually solvable. And so it's a statement of well-behavedness for groups, and It's also known, due to the work of McCarthy, that mapping class groups satisfy a Tietze alternative, and due to the work of Bestvina, Fein, and Handel, in the case of outer automorphism groups of a free group. And so the basic idea of this proof, or of Tietze's proof of the Tietze alternative, which was replicated in these other two states, these other two settings, is find some geometric space where your group acts, attempt to play ping pong with the subgroup. If you can find some invariants which allow you to play ping pong, you have a free subgroup, and then argue that if you can't play ping pong at all, you satisfy some sort of solvability condition. That's the broad outline. McCarthy, in his proof of the Tietze alternative for the mapping class group, proved the following related but not sharper nor equivalent result. So this is due to McCarthy. And McCarthy proved that for sigma and tau in the mapping class group, there exists an n such that the subgroup generated by the nth powers is either free of rank 2 on the nose, or their nth powers commute. So this is not equivalent to the Tietze alternative. And you can take, for example, take the order 2 and order 3 matrix which generate SL2Z. This theorem tells you take n equal to 6 and you get the trivial group, or you get that their identity matrix commutes. But they also generate they generate all of SL2Z, which contains a free group. So this is a different statement. So either their nth powers generate a free group, or, oh, I wrote down a commutator, but I didn't write down what the commutator is equal to. Or they commute. The commutator is equal to 1. So this is McCarthy. And now, later work, so this n in McCarthy's proof depends on sigma and tau. I guess I'll come back over here. I don't have enough board space to keep this up. So here, this is McCarthy's theorem. It's not true. So later work, and this is due to Hamidi-Tehrani, and then Fujiwara and Mangahas show that n can be picked independent of sigma and tau. So Hamidi-Tehrani proved this statement for Dane twists. Fujiwara proved this for pseudo-Anosov elements of the mapping class group. And then Johanna proved the relative case interpolating between the two. So for partial pseudo-Anosovs and things that are partly partial pseudo-Anosov and partly Dane twist in different places. So this was a uniformness statement. So I'll say yes and uniform. In GLNZ, well, it's just not true. That's kind of sad because this is supposed to be an analogy, and my dictionary now has a no and a yes. And what is the problem? Well, you have things that are solvable but not abelian. 1, 0, 0, 1. But Broglie and Gelander get a related statement. Since I'm not really here to talk about linear groups, I'll just say kinda in scare quotes and leave it at that. You can talk to me after if you want to know the specific statement.
So it's not, if your Tietz alternative produces abelian groups,
Yeah.
it might be a reasonable question in general, but it's not really reasonable for GLNZ.
Yeah, it's not really a reasonable question for GLNZ. Broglie and Gelander formulate the correct reasonable question and prove that the answer is yes.
Okay.
So it's specifically, well, I guess I'll say it, but I won't write it. Specifically, it's there is a uniform n, so that if you look at the set of n-fold products, so the set of words of length n in your two generators, either there are two things in there that generate a free group, or the group generated by all of the words of length n in your two generators is immutable. So that's sort of the right statement. But I came to talk about outer automorphisms of free groups, and it's a big question mark. Does a McCarthy theorem hold for the outer automorphism group of a free group? And so, conjecture is yes, but don't have an answer. And before I can state some partial results, I want to state a bit of terminology for dealing with the outer automorphism group and point out its analogy with mapping class groups. So, some definitions. Sigma and outer automorphism. The growth of sigma is this function, f of n equal sigma to the n w. Sorry, that's not how I want to state this. Sigma is polynomially growing. In the talk title, I talked about linearly growing ones, so replace polynomial with linear. Is polynomially growing if the word length of nth iterates with respect to some basis of the free group is bounded above by, I guess I'll say is a member of O in n to the d for all group elements. So I guess I should really say conjugacy classes, since this is an outer automorphism, but I'm going to be sloppy about that because it's a talk. And then sigma is exponentially growing if there is a w so that this is bounded below by some lambda to the n. You can get much more precise and understand the growth rates of exponentially growing things, but I will not be talking about that today. And so this is where we are. This is our motivation. It's this question mark, and I'm going to talk about some partial results. Oh, need one more family of outer automorphisms, sorry. Sigma is fully irreducible if no conjugacy class of free factor rank greater than or equal to 2 is sigma periodic.
Lambda is independent of the...
So lambda is some basis. It turns out that... in this? Yeah. This lambda depends on the automorphism. So if there is a w...
But it doesn't depend on...
And a lambda. It could depend on w. But if this is true for some w, this is not true for any w.
Right. I'm saying
Yeah.
it's not like the length of W, this lambda.
It is not like the length of w times lambda. Oh,
Lambda is not the length of W.
lambda is not the length of w, no. Lambda is some exponential growth rate.
Okay.
Oh, it needs to be times, sorry. You're correct. I need to normalize by the length of w.
Oh, okay.
Yeah, there we go. So it's fully irreducible. So in the analogy with mapping class groups, the fully irreducibles are the ones that behave like pseudo-Anosovs. One example is you take the image of a pseudo-Anosov on a punctured surface with the free group of the appropriate rank into the outer automorphism group of the free group. Polynomially growing things are the ones that behave like reducible outer automorphisms, but they have behavior that doesn't have any analogy with surface theory, and we'll see some examples of that subsequently. And exponentially growing things you can think of as pseudo-Anosov on a subsurface, but once more, there are phenomena that are just non-surface phenomena that we'll have to deal with. Well, in this talk we won't, because we're talking about linearly growing things. So this is a summary. Here's a list of partial progress on a McCarthy theorem for out fr. So Vestvina, Dane, and Handel say yes for sigma and tau fully irreducible. So in the pseudo-Anosov case, things behave appropriately. And there's a new proof by Kapovich and Lustig. Lee's student Pritam Ghosh showed that if sigma and tau are exponentially growing and satisfy an incompatibility condition, and I don't want to state it because it's a bit technical, then they have a power which generates a free group of rank 2. Be alarming if the free group of higher rank was 2 generated. My colleague Sam Taylor, for a different incompatibility condition, sigma and tau exponentially growing, incompatible. But I won't, once again, it's technical and I won't state it, just that it's different. Sigma to the n, tau to the n generates F2. In fact, Sam gets a little more for, well, Sam gets a little more. He also gets the other side of the McCarthy theorem he characterizes as commutators in his special case. The negation of his compatibility, of his incompatibility condition gives a compatibility condition, which implies that the two automorphisms commute. I want to make sure I don't slight anyone. No. So that's sort of, that is all of the partial progress for things that are exponentially growing. Over on the linearly growing side, Clay and Pettit show that if sigma and tau are linearly growing and fill, then they generate a free group. And Funda-Gultepe showed that if sigma and tau are far apart, so far apart means that they have well-separated elliptic fixed points in their action on the free factor complex, if you know what that is. If not, it's one of these geometric spaces that the outer automorphism group of a free group acts nicely on. Linearly growing things are elliptic there, and far apart means their fixed points are well separated. If their fixed points are well separated, this is a familiar ping-pong argument, they generate a free group on the nose. So that's kind of nice. That's getting back towards one of these uniform power type things.
After this result from Dane and Handel,
Yes.
is sigma and tau, all of these sigma and taus are fully irreducible?
No, this is the only one where they're fully reducible. Here, they're just exponentially growing. They may have some kind of reduction system. Here, exponentially growing, but may fix some free factors. Here, they're linearly growing, so definitely not fully irreducible. And here, also linearly growing. So towards the other side, so these are all, for the most part, free group generation results. In the other direction, Cohen and Lustig characterize when sigma and tau linearly growing have commuting powers. And at this point in the talk, you might say, hey, wait a minute. Like, can't you just say this and combine it with either this one or this one? And is that all you're going to say? No. Cohen and Lustig's compatibility condition, which I'll revisit a bit later in the talk, the negation of it is not the statement of either far apart or filling. So there's something to prove, and that is what I do. So here's the theorem. Me. And so I also want to point out, and this is especially for Lee, who's heard a version of this talk before, this is what's new. Set n equal to 48 r squared minus 48r plus 3 times the rank of GL R z mod 3z. For linearly growing, sigma and tau in the outer automorphism group of a free group of rank R, either sigma to the n, tau to the n is free of rank 2, or they commute. Their nth powers commute. So the n here is uniform. It depends only on the rank of the free group and not on sigma and tau, which is similar to the later work of Hamidi-Tehrani on the McCarthy-type theorem. So it gives hope that there's some uniformity in the outer automorphism group, and none was previously known. So this number looks kind of funny, especially like what is the rank of this group doing here? Well, the rank of that group comes in outer automorphism groups, like mapping class groups. There's some amount of finite ordered behavior, which causes, instead of you having some sort of invariant system which you can decompose your automorphism, you have a periodic system, which the periodic system is invariant, and you want to pass to a power where it's actually fixed. And so here's the fact due to Cohen and Lustig. And Lustig, and I think that they knew the power, but the exact power that you need appears in the second paper on the Tietz alternative by Basvina, Fein, and Handel. If sigma is linearly growing, outer automorphism of rank R, then sigma to this order is what we call a Dane twist. So what you should think of for a Dane twist is the image of some surface with fundamental group of free group into the outer automorphism group of a free. So the image of the mapping class group of a surface with the correct fundamental group into the outer automorphism group sends Dane twists in. That's what you should think of. This is what they are. So linearly growing things are all roots of Dane twists. But there's a purely algebraic definition of Dane twist. And we need this algebraic definition to make sense of, Dane twists which come from different surfaces and cannot be realized simultaneously on the same surface. If you're wondering, like, what's an example of those, one will appear. But to talk about algebraic Dane twists, I need a crash course in Basse-Serre theory.
Can I just ask a quick question?
Absolutely.
All these results seem to, does one ever consider a case where sigma is linearly growing and tau is exponentially growing?
I would like to. One needs to prove the full statement. I don't know how to deal with those cases. And if someone in this audience does, like, let's talk. Yeah. One would like to. One should. In Johanna Mangahaus's result, which I mentioned, which is the uniform version. So in McCarthy's result, he considers the case of a pseudo-Anosov versus a Dane twist, or a partial pseudo-Anosov versus a Dane twist. So to get the full conjectured statement, you will eventually have to do that. So far, I don't know how. And I don't know anyone who does. And if you do, I would like to talk to them. So to say what a Dane twist is, I need to give you a crash course in Basse-Serre theory. If you're not, well, let's see here. There are a lot of graduate students in the audience. Have you all done the good graduate student thing and spent an afternoon or a week or a month or a career looking through Serre's trees and enjoying it? I see some nods. I'll give a crash course. You should really do that. It's a great, at least the afternoon and probably the week, if not the career.
So if I understood right the Dane twist, so your algebraic definition amounts to saying that there exists a surface.
There exists a surface.
Fundamental domain is
with
fundamental group is FR, such that the image is.
Yeah.
But you can't choose the surface.
Yeah, you don't get to choose the surface, and that's the problem.
Okay. Yeah.
It would just be McCarthy's theorem if you could make the surface be the same.
Right.
And there are examples where you just can't do that. And so that explains where this number comes from, and the rest of it is actual work. So I'm not going to prove the theorem. I'm going to prove the thing that implies the theorem, which is prove the theorem for Dane twists and this power. And then by tacking on this extra bit, you get it for all linearly growing ones. So crash course in Basse-Serre theory. How do I want to present this? So this is a generalization of Van Kampen's theorem, but that sells it kind of short. So definition, a graph of groups, gamma is a graph, which I'll also call gamma. And on each vertex and edge, a group denoted respectively gamma v and gamma e, and inclusions of the edge groups into their terminal vertex groups. So I'm going to think of an edge as an oriented edge. Its reverse will be denoted E bar. So every topological edge in your image of a graph is really two combinatorial edges. This is Serre's convention. And the first time you see it, you might say, this is not a good convention. And then you'll spend the rest of the afternoon trying to do it the other way. And it doesn't work. So I mean, it does, but the notation gets worse. So here's an example of such a thing. Well, take a surface. Oh, No, yeah, I can do that. Take a curve. Van Kampen's theorem says that this, so far I've written down a graph of groups and I haven't told you why you should care. Well, it's sort of a way of recording all of the data of Van Kampen's theorem. So the vertex groups are the fundamental groups of the two pieces. The edge group is the fundamental group of their common annulus. And so definition, the fundamental group of a graph of groups, so pi1 of gamma, and you need a base point, but I'm going to suppress base point issues, is the fundamental group of gamma is the fundamental group you get by gluing together Eilenberg-MacLane spaces for the vertex spaces, the vertex groups, and the edge groups, KE, according to the inclusion maps. There's also a definition of this group entirely in terms of edge paths in this graph, decorated after each edge with some element from a vertex group here or a vertex group here. Or if it's a more complicated graph of groups, you've got like a complicated edge path and there's decorations all the way along. But this definition allows me to completely avoid any of the combinatorics of the edge paths. Give a topological definition of a fundamental group. And so in this case, the fundamental group of this graph of groups is just the fundamental group of this surface. And now, OK, who cares? Like, this seems like a whole lot of stuff. But the great thing that it lets you do, and this is a fact, sort of a combinatorial covering space theory, is the fundamental theorem of Basse-Serre theory. And it is graphs of groups gamma correspond one-to-one. Graphs of groups of gamma with the fundamental group of this graph of groups isomorphic to G correspond one-to-one with G actions on simplicial trees. And so we can turn this picture where these, so if you actually write this down with generators and coordinates, you had to like pick a fundamental domain for the lift of this to the universal cover of the whole surface. These combinatorial expressions can look really different, even though they give you the same tree, even though they give you the same action on a tree. And it's because these labels are only defined up to conjugacy. And it's very easy to write down two graphs which look really different but are the same tree. And I know this because Lee did this during my defense. And it took us a while to figure out that they were the same. So if you write down two trees and they look different, probably they're the same, and ask me afterwards and we can work through it. And so it also lets us understand geometrically through this group action on a tree combinatorial statements about word lengths. And so definition, the translation length in a tree of a group element G, so T is a tree with G action. This is LTG is the min over all points in the tree. And I'm using min because it is realized of the distance that G translates X. And another nice fact, if you work out the normal form theory, say this edge path, the translation length in the tree of a group element gamma is equal to the cyclically reduced edge length, or edge path length in the graph of groups gamma. Oh man, this is getting really sloppy. Gamma, which I'm going to say the graph of groups corresponds to an action. I'll just write it as a quotient. It's not, well, it is a topological quotient, but the graph of group structure comes from thinking of it as an orbifold quotient. So this brings us to Dane twists. I'm going to keep this example up. So in this example, if you look in the universal cover, you've got a whole bunch of lifts of this curve. You have a whole bunch of connected components of the complements. And where is the tree? It is the dual tree to the system that you get by taking all of the different lifts of this curve to the universal cover. And maybe I'll draw that picture. So here's the lifts of the curve, and then here's the Basse-Serre tree. And I've only drawn finitely many lifts, but this curve has, for each twist, there's each vertex is infinite valence, because there's a whole bunch of different things. Well, I don't want to go to the same component, though. There's a picture of a piece of the Basse-Serre tree of this splitting. A schematic, really. So this brings us to Dane twists and compatibility. So what good is this? Well, it gives us a uniform algebraic way to define Dane twists. So a Dane twist on a graph of groups gamma is, and I guess I now need the normal form, so about edges. So you pick a set of edges. This should be thought of as picking a set of curves. Edges in the edge set. And now you pick a system of twistors. So that's Zi in gamma EI. And this needs to be closed under, I won't worry about the technical, it won't matter too much. So a Dane twist, you pick a set of edges. This is like picking a set of curves. You pick a set of twistors. This is like picking a set of twist powers. They need to actually be in the center of the edge group. But all the splittings we'll look at are cyclic, so that's a redundant condition. Is the map. Group elements can be represented by edge paths, so I'm going to tell you what it does to edge paths. This twist, EI, for an edge in your edge set, multiplies it by Zi. For everything else, so I'll just write G. And this is EI in your collection. In this example, if I wanted to do the Dane twist about this curve, I would have edge set consisting of this edge and its reverse. So I need to have this edge. And then I have some fundamental group element representing this twist, this curve. There's a choice of orientation, so you have a choice of generator. That's all subsumed in picking Zi. Some number of twist power, forward or backward, depending on the orientation you've chosen. That's the data. And if you go through and carefully write down what it does at the level of fundamental group using the splitting that you get in Van Kampen's theorem, you can see that algebraically this is doing exactly the correct thing. And so that is our Dane twist. Why do we do it at the level of trees as opposed to the level of surfaces? Well, because we want to be able to compare Dane twists that came from different surfaces. So this is my definition of a Dane twist. So this is a problem with this definition. It's wildly non-unique. You could pick a bunch of different graphs of groups such that the action of this on the fundamental group induces the same outer automorphism. So This is fact due to Cohen and Lustig. Every Dane twist in out of FR has a unique good, where I don't need the definition of good, a unique good known in the literature as efficient, or they gave it another, normal. Unique good graph of groups representative. And so now I mentioned that Cohen and Lustig gave this compatibility condition. I can now tell you the precise statement of the compatibility condition. So this is a lemma. So sigma is a Dane twist with good rep on a graph of groups, which I'm going to call A bar. And tau is a Dane twist with a good rep B bar. And now suppose that at the level of trees, there is a FR tree, T, and these are equivariant surjections which collapse edges. Okay, this is a hypothesis, but let's unwind what this hypothesis is. So sigma is the Dane twist in the outer automorphism group of a free group. It has a good representative according to Cohen and Lustig, which is a graph of groups. The graph of groups has a Basser tree A. Ditto tau has some Basser tree B. And if there is this common tree T, which equivariantly is a common refinement, and in the picture, you should think of the Basser tree of this splitting, the Basser tree of the yellow splitting, and the Basser tree of the union of the two curve system. That gives you a collapse. In the surface setting, what happens? Well, the two Dane twists about those curves commute. But you can see that entirely at the level of trees. So with this hypothesis, sigma and tau commute. So that's Dane twists and compatibility. And I don't need this example anymore. And so what you would like is that well, you just negate that condition. Say there does not exist a tree, and you're off to the races. So one case, so this is lemma me, and also Clay and Pettit, although they don't get the uniform version, so on uniform. So now, how do I state this? So a sufficient condition, sorry, I did this too soon. A sufficient condition for no refining tree is, and I'll just draw it by example. Here's my graph of groups. A, B bar. So for one edge, I'll restrict my attention to one edge trees. So a sufficient condition for these two one edge graphs of groups to not have a common refinement is that the length in the A tree of the edge stabilizer B is positive, and the length in the B tree of the edge stabilizer A is positive. In the case where these are curves on the same surface, what this is saying, each of these lengths is equal to the intersection number of the two curves. In general, we don't have a surface to argue on, and so we say that we look at the translation length of the splitting element of one tree in the other tree, and that gives us a sufficient condition. And now the lemma. When sigma and tau are twists on trees, B. Clay, Pettit, non-uniform. So when sigma and tau are twists on trees with one edge and clashing lengths, so this is what I mean by one edge and clashing lengths, then n equals 48r squared minus 48r plus 3 gives our free group F2, and the proof. Oh my goodness, am I actually going to try and prove this thing? No, I'm going to write down for you. So the proof is using the ping-pong lemma. And so I'm just going to write down for you the ping-pong sets and say some words about where uniformity comes in. And then we won't get to the bad examples, but that's not too bad. So my ping-pong set is going to be the set of words in the free group that have positive length in both trees, or have positive length in at least one of the two trees. So if you're thinking by analogy with surfaces, this is, I'm looking at the set of simple closed curves that cross either one curve or the other curve. And now the ping-pong set for sigma is going to be those conjugacy classes in my ping-pong set. Which, oh, I always get this backwards. I'm talking about this for a while, I still get it backwards. So epsilon is, well, I'll just use the square root of 2. Square root of 2. LAW. Occurs to me that I've been talking about translation lengths in metric trees, and I never told you what the metric was. There's simplicial trees. I'm using the length, the metric where every edge has length 1. So it's the edge path metric. So these are the ones that cross B more than they cross A. And p tau is the complementary set. And so the things that cross A more than they cross B, what does the square root of 2 have to do with it? Well, these are integer valued, and I need to decide which ones, where the equal ones go. So I multiply by an irrational number and make it a true partition. And now my claim is that, well, if I apply a large power of sigma to something in here, it's going to end up in here. And then, in particular, I can get a precise estimate for what large enough means independent of sigma. And why is that? Well, if you have positive length in the A tree, that means that your normal form with respect to this A graph of groups crosses the edge back and forth. And so you have to be now a bit careful because there could be some cancellation. But when you apply a large power of sigma, sigma is twisting by some power of A, you get a whole bunch of A's. But by hypothesis, A has positive length in the B tree. And so the B length is going to grow linearly with sigma, iterates of sigma. But sigma, the Dane twist, A is elliptic. And so it's a fact that the Dane twist's action on group elements, or action on trees, fixes its defining tree. So this stays constant while this grows linearly. And so you end up over here. And now when you're estimating the linear growth rate for this, it turns out that you want to use the bounded cancellation lemma, which is or a form of the bounded cancellation lemma, which tells you that when you're sending a simplicial free tree into, you have a map from a simplicial free tree into some tree with free group action, maybe not necessarily free, not necessarily simplicial, you have some control over the image of geodesics and their lengths. But you need to pick which source tree you're using. And the uniformity comes in from, in this ping-pong argument, you can always, to estimate the length, the growth rate of lengths in B, you can always pick a tree that's well adapted just for the B. Pick a tree for applying bounded cancellation and making the estimate that's well adapted for the B tree. And that gives you your estimate to show that sigma, powers of sigma take elements in the tau set here. When you're going the other way, you can pick a different tree. And you can pick a tree that's well adapted to estimating growth in A. And because you can pick the tree, always your favorite tree, then it's just a question of what's the best, you can get the best tree to be and what the bounded cancellation constant is and the technical details.
So you're saying one particular A tree for A, one particular tree for B, and then it's just the bounded cancellation constant between those two trees.
Yeah. But you get a free choice of the two trees. And so you can always pick them to be well adapted. Well, at least you can pick them to be this well adapted. So I promised you some examples of some non-surface things. I won't talk about the ping-pong sets. I'll just give you two graphs of groups. So these are H and N extensions of the H and N splittings of the free group on 3 generators, the Dane twists around which. So A is the stable letter of the extension. The edge stabilizer is B in this one. And here, A, these don't fit into the framework. CA, CB. So a Dane twist, so this pair of trees does not fit into the framework. The translation length in this tree of B, well, it's in a vertex stabilizer, so it's 0. Translation length in this tree of C, also in a vertex stabilizer, also 0. Nevertheless, if you work out, you can work out that the twist about this tree, twist about the A edge in this tree by B is the Nielsen transformation. A goes to BA, everything else gets left alone. This one is A goes to CA, so they obviously generate a free group. And so this sufficient condition isn't necessary. I don't have time to state the sufficient condition, but you can make it work in this case. And in fact, in this case, the n that you need is 3. Totally independent of rank even. But I don't have time to say anything about how you actually deal with this case or how you prove that cases like these, cases like one other one, and the case I've presented are the 3 possible cases. So I'll stop here.
Questions?
I see. So this was just the Clay-Pettit part and how to uniformize that one.
Yeah.
Okay.
The polynomially growing part, or the part where the subgroup generated is purely polynomially growing. These bad examples part was already uniform. What I think is really interesting, and I think it's a subtle and difficult question, Funda-Gultepe's result is n equals 1 when the 2 Dane twists have well separated. The amount of separation depends on the rank of the free group. And then you've got this intermediate range where it's uniform, but the power depends on the rank. And then these examples, and the ones like them, are all bounded distance. Well, the pair of fixed points is a small, it's like 2 in the free factor complex, or 1. It's like these have adjacent fixed points. And so when you have adjacent fixed points, it's uniform independent of rank. When you're really far away, it's uniform independent of rank. In between, the best we know is that it depends on rank, but it seems like it shouldn't. So in the mapping class group, Hamidi-Tehrani shows that for Dane twists in the mapping class group, n equals 4 works. Any genus, any Dane twists, group generated by their 4th powers. Well, if they don't commute, then the group generated by their 4th powers is free on the nose. It'd be kind of cool to get this n independent of rank, but I don't know how to do that. Because this argument is essentially Hamidi-Tehrani's argument using length functions in place of intersection numbers. And if you want to estimate length functions, you need bounded cancellation. And if you want to use bounded cancellation, somewhere in there, either in the Lipschitz constant or in the tree volume or in the metric, you have to pay a factor of the volume of your tree, which is the rank.
Something I don't quite understand is, given that you have a certain n value for F2, but you have these subgroups of F2, like F3, F4, etc.
Mm-hmm.
So I don't understand how that's, like, I don't quite understand how n depends on R, given that.
Ah, right. This F2 is just these two things generate a free subgroup of the outer automorphism group of FR. Sigma and tau live in the outer automorphism group of the free group, fixed free group FR.
Oh, okay, I see.
Yeah.
Okay.
This F2 is not the F2 that we're in out of.
Okay, I see.
Because in the case of out of F2, that's GL2Z. This theorem is known. Yeah.
All right, let us thank Edgar again.